They say a factory at night has a temperature all its own. Not just the heat of furnaces, but a pressure that sits in the air like fog. The cameras find it by the glow through the windows, orange, relentless, as if the building were a living thing, exhaling light. Inside, a single hand reaches for a cold, cracked sliver of metal, lifts it to the light, and, soot streaking the knuckles, presses a thumb into the hairline fracture as if feeling for a pulse. That hand belonged, in our reconstruction, to Frederick Brackett, a chief metallurgist whose life up to that moment had been measured in lab notes, breathless test runs, and nights when the town slept and the plant did not. They told him it couldn't be done. The metal told him otherwise. The problem was not romantic. It was arithmetic, physics, and exhaustion. The Army needed bombers that could fly farther and carry more. Range and reliability were the axes on which strategy turned. Distances over the Pacific were unforgiving. The B-17, for all its wartime fame, reached limits dictated by wing strength, by weight distribution, by the ability of joints and spars to survive repeated flexing and vibration under combat conditions. Every pound of payload or gallon of fuel demanded structure that would not fail. And when a wing failed, the loss was immediate and brutal. Pratt & Whitney's plant, one of the humming industrial hearts of Connecticut, had been running at capacities that would have seemed obscene in peacetime. 3 shifts, machines that never cooled, test cells that eventually vibrated on their mounts like caged beasts. Men and women worked the seam between what the book said could be done and what the war required. Brackett, trained in metallurgy, kept a ledger of failures the way a pilot keeps a logbook. Date, specimen, fracture mode, ambient conditions, the sound the brake made, brittle, granular, ductile. He treated metal like an interlocutor. He listened. At first, the questions were small and material. Rods would split under torsion. Cast fittings developed hairline cracks along bolt holes. A spar that should have held double its measured tolerance cleaved on the test stand after a run that, on paper, should have been trivial. The test cell doors had become a fixture of anxiety. On one night, a cell door blew open when a casting fractured. Windows on adjacent lines rattled for a minute afterward. They got lucky that no one stood directly in the blast path. The air was littered with tiny metallic shards and a collective memory of risk. This is not a single invention story in the romantic sense. It is a string of nights and experiments stitched together by a stubborn human insistence. But if we are to place a human face on those hours, Brackett's is the one most often reconstructed in plant records and recollection, a man who spent hours in the lab after meetings, who wrote postcards to his wife with a single line about being tired but hopeful, who argued softly with production foremen who wanted immediate scale-up and with engineers who wanted more theoretical proof. Whether his was the only hand involved is indefinito. What is clear is that one practical, iterative mind became the pivot on which a crucial method took shape. If you care about the people behind machines, if the quiet, stubborn work of craft matters to you, take a moment now and like this video. It helps preserve stories the headlines miss. The plant made engines, but the physics of metallurgy did not respect departmental boundaries. The same problems that plagued crankcases and impellers, fatigue, stress concentration, thermal gradients, surfaced in spar forgings and fittings. Brackett and a small team of metallurgists and machinists began to view the wing as a complex assembly of metal soup and fractures rather than a single, immutable structure. The key, they decided, lay less in brute force and more in direction, how the metal was formed, how it cooled, and where residual stresses accumulated. Samuel Ortiz, a young mechanic with grease permanently etched into the ridges of his palms, became Brackett's eyes on the floor. Ortiz had lost part of 2 fingers on a previous job. The scar tissue on his left hand moved in a particular rhythm when he cleaned a forging. He had an ear for machinery and an eye for the little anomalies others dismissed. Harold Wentworth, the draftsman, sketched the ideas that the engineers considered too rough to print. Airflow patterns through a cooling chute, the way rivet placement altered a stress path across a spar web. Together, they were a makeshift mind, a metallurgist, a hands-on mechanic, a designer with a pencil that never stopped. They began by cataloging failure modes with a forensic intensity. A fractured sample from a wing lug would not just be thrown away. It was photographed, cross-sectioned, and then etched in acid so the grain structure would reveal its history like tree rings. Patterns emerged, small inclusions acting as nucleation points for cracks, directional grain alignment that accentuated stress when bending forces aligned against the grain, microvoids seeded by washing agents or casting flux. The plant had been designed to be efficient, but the scale meant that a single design choice, a cooling rate, a vibration fixture, a polishing technique, could have cascading effects. One early breakthrough was mundane, the discovery that certain fastening holes acted as stress concentrators not only because of their geometry, but because of how they had been cooled after drilling. Drill-generated heat, followed by rapid quenching and cold oil, introduced tensile residual stress around the bore. Those tensional rings liked to open when a wing experienced repeated cycles of loading. Brackett's notebook noted in a cramped hand, heat path dash quench temp differential equals ring tension. The solution could have been simple. Temper the bore, adjust the quench. But the simplicity was deceiving. Changing the cooling regime for a single part threatened production quotas in a plant already balanced on razor-thin lead times. They tested a range of alloy tweaks. Aluminum alloys at the time were a careful chemistry. Copper, magnesium, manganese in various doses created trade-offs between strength, brittle behavior, and corrosion resistance. Brackett pushed compositions to a point where they gained fatigue resistance at the expense of machinability. A test batch that looked promising on paper clogged press tools and slowed lines until foremen grumbled that the plant could not afford metallurgical experiments. Yet when a treated sample endured repeated flexing on the rig, men who had been skeptical lifted their heads. But alloy changes alone were not the method. Heat treatment cycles, sequences of heating, hold times, and controlled cooling were their laboratory's darkest arts. They built furnaces that could maintain higher temperatures with less fluctuation, but the real innovation lay in staged cooling. In several reconstructed runs, the team would heat a spar blank to a high soak temperature, then move it to a controlled chamber where airflow was directed in a pattern that favored certain grain orientations. The idea was not to lock in strength through brute cooling, but to coax the metal to adopt a microstructure less prone to crack initiation under alternating loads. It was a kind of metallurgy by suggestion. Encourage the metal to orient its internal lattice in a way that would better distribute stress. The plant itself became a laboratory of extremes. On some nights, it felt like a besieged outpost. Crew rotations were tightened, ovens ran until their linings flaked, and the smell of flux and heated alloy layered over the usual industrial scents. Workers slept on bunks in the boiler room or in their cars. Letters home were short and earnest. One woman, whose name appears in a reconstructed diary entry, wrote to her husband, "You sound tired. Come home when they let you." That message hung over the lab the way a cautionary poster hangs over a lathe. A human counterpoint to the experiments. A reminder that each incremental improvement would arrive not in a vacuum, but in the lives of families and crews. Failures were theatrical and costly. A full-scale spar test once developed a crack that started in an arc rivet line. The test stand groaned. The sound was described later by workers as like a ship taking on water. The specimen failed after 1,282 cycles, a number that became infamous on the floor, because it taught them that life is measured not in single catastrophic events, but in repetitions. Each cycle burned a little metal memory into the part, and when resonance aligned with a geometric weakness, everything gave way. They began to test not just how much force a part could take before breaking, but how micro-vibrations compounded damage. Vibration testing, with shakers that could simulate the flutter of a wing under airflow, became a central part of experimental runs. Here, Harold's draftsman sketches mattered. He proposed small stiffening ribs in targeted locations that could alter the natural frequency of a panel, nudging it away from resonance conditions that led to fatigue. It was a subtle approach, a small change in structural topology, producing outsized gains in endurance. But production engineers viewed it nervously. More material here, fewer fasteners there. The changes had to be proven before a single wing would be signed off. Around these trials, personality clashes flared in the fluorescent light. Production chiefs wanted replicable instructions to scale. Military liaisons wanted assurances that aeroplanes fitted with new parts would fly the missions commanders demanded. Brackett, precise to the point of stubbornness, traded impatience for rigor. He insisted on charts, on control specimens, on capturing the exact quench rate in degrees per minute rather than quick or slow. This meticulousness earned him respect and made him exasperating. One scene, reconstructed from employee testimony and lab notes, captures the tension. It is late, the blast furnaces hiss. A new batch of spars sits cooling on trolleys. Brackett walks the line, clipboard in hand. Ortiz is tightening set screws with a wrench that has polishing where his hands typically slide. A foreman says, "We've got an order for 60 wings by Friday. You can't keep tinkering." Brackett, without ceremony, replies that an unsafe wing is worth nothing to anyone, and if those wings return buckled in the Pacific, the plant will make headlines for the wrong reasons. Reconstructed dialogue. Foreman, 60 wings, Friday. Brackett, 60 unsafe wings don't keep a man alive. We fix the cause or we don't ship. Ortiz, softly, fix the thing, Freddie. Such exchanges were not mere theatrical, lady. They translated into decisions, whether to throttle back production by a shift to allow preheating of blanks, whether to change rivet schedules, whether to install acoustic microphones on test rigs to listen for the beginning of crack propagation. The latter idea, audio forensics, came from an unlikely quarter. An old tool and die worker who compared the subtle difference between a fatigue crack's rasp and a brittle fracture to the difference between the screech of a chalk on a blackboard and the dull snap of a twig. They began to record test runs and catalog the sounds. On certain recordings, at precisely 0.43 seconds before catastrophic failure, a high-frequency squeal would appear. It gave them a potential early warning signature. It is tempting to compress this into a moment, the one night where everything finally aligns and the impossible idea appears fully formed. But history rarely yields to a single lightning strike. The impossible method grew as a composite, an alloy formulation that dealt with inclusions, a heat treatment sequence that guided grain orientation, a controlled cooling system with directional airflow, a fastener layout that redistributed stress, and a non-obvious process step, a peening or surface treatment that introduced compressive residual stress at the surface to inhibit crack initiation. Each element had precedent or analogs in other parts of the plant. The leap was in combining them for structural components that bore bending loads for hours on end. There were near disasters during the trial runs. In one reconstructed test, a full-size spar undergoing the new regimen survived the initial cycles only to develop a longitudinal crack beginning at an edge where a prior handling nick had removed a hair of material. The test stand alarm screamed. Water misted the part to cool it and stop the spread. Men ran breakers with faces lit by red emergency panels. They had to decide whether to stop the test and risk losing the data, or to let the run continue in the hope the changed method would arrest propagation. Brackett argued for the latter. Let the part run until failure to see how the new method shifted the crack's progression. That decision netted critical data. The crack, when it did run forward, behaved differently from earlier specimens. It progressed slowly at first, not in a clean snap, but as a grinding, messy spread that left internal grains elongated and plasticized instead of brittle and granular. The conclusion drawn in the lab, the method introduced a ductile response in conditions that previously produced brittle failure. That was the sort of outcome they had chased. All of this, however, existed in a larger moral and strategic frame. The products that left the plant fitted to B-17s or other bombers would almost certainly be used in missions with deadly consequences for those on the ground. Brackett, an engineer with a craftsman's heart, kept a ledger not only of specimens, but of letters from crews, notes of thanks when a damaged airframe staggered home. He kept, too, a stack of press clippings about raids and distances, and he visited at times the quiet areas of the plant where workers folded their hands and prayed. There was no joy in enabling destruction, and yet there was a conviction, uncomfortable, necessary, that improving reliability saved lives too. The crews who could bring their aircraft back because a wing held where it previously might have failed. In the background of their work, a larger political urgency pushed faster than the science could comfortably move. War planners demanded shorter turnarounds and more assurances. Plant directors spoke of deadlines measured not in weeks but in sorties. Government inspectors visited, their badges and clipped speech a reminder that failure could become scandal. Brackett, mindful of these pressures, navigated a narrow corridor. His reputation, the lives relying on the parts, and the integrity of his science. He refused to sign off on processes that had only anecdotal validation. He insisted on documented, repeatable evidence. He believed that for a method to be accepted, it had to be demonstrable under the most unforgiving tests. Yet the human cost of such rigor was not small. Workers strained their hands. Some developed respiratory complaints from the fluxes and solvents used in cleaning, and one young technician collapsed from heat exhaustion after a night of monitoring runs. The plant instituted mandatory cool-down periods and rotated men more frequently, but not before murmurs of fatigue, resentment, and fear flavored the air. The war compressed ethical decisions into the rhythm of shifts and runs. How long to press an experiment, when to pull it, and how to weigh a life against a marginal gain in endurance. By late winter in our reconstruction, the team had reduced the variables to a plausible sequence. They referred to it quietly as the method in notes and fragments. A defined alloy batch, a soak and slow cool schedule that favored elongated grain flow, a directional cooling stage with controlled air jets, surface peening focused on rivet lines, and a slight redistribution of rivets that altered local stiffness. The method was not a magic incantation, but a recipe with many sensitive steps. It required skilled hands to reproduce and a tolerance for slower production tempos. Scaling any new metallurgical regimen is where laboratory romance meets industrial reality. The plant's presses, dyes, and worker habits had been optimized for existing sequences. Introducing a controlled cooling chamber between pressing and trimming meant rearranging lines, retraining crews, and, crucially, convincing the people who wrote paychecks that the change would not bankrupt production quotas. Brackett found himself, increasingly, in meetings he never wanted. Budget hearings, written affidavits about safety margins, and painstaking explanations to men who measured success by units produced per shift. And yet, small victories accrued. A batch of treated spar assemblies survived a vibration regimen that had previously caused panels to fail in the thousands of cycles. A field report arrived, terse and thrilled. A bomber had returned from a long-range mission with a damaged wing section that, under prior construction, would likely have torn away. The crew credited luck and good iron, but the engineers in the plant read the report as a tentative validation. The question remained, was the correlation causal? Could they confidently say the method had done the saving? The answer, in strict historical terms, was indefinito. The engineers knew better than to trust a single event. Tension in the plant increased. Some believed the method was ready for full-scale adoption. Others argued that more tests were needed. The War Department wanted assurances, and the plant's board wanted a green light to push the new steps across the assembly lines. Brackett, whose voice carried the authority of data and the weight of nights spent cold in the lab, proposed a staged rollout. Begin with a pilot line, instrument every component, and compare field failures across matched control groups. The plan satisfied neither the board's desire for scale nor the tough requirements of the military liaison, but it was defensible. As part one of this story moves toward its midpoint, we watch the plant breathe in a collective intake. Machines were retooled, a cooling corridor installed where forklifts now curved slowly between racks, and a new set of glass-covered data tables emerged where charts could be read by daylight without smudged ink. Worker schedules were adjusted. Brackett held briefings at dawn, before the lines heated, explaining not only the steps, but the reasoning. If we understand why the metal behaves, we can control the outcome, he told them. We are not guessing, we are documenting. The team prepared a full-scale test under controlled, instrumented conditions, not a spar on a bench, but an assembly that would see torque, bending, and cyclic loading to represent the brutal reality of a bomber wing over a long mission. The test rig was an engineering theater. Hydraulic actuators, strain gauges dotting the skin, accelerometers, and high-speed cameras trained to catch the exact moment when microcracks, unseeable to the human eye, betrayed their presence. Men who had stood through explosions now held their breath as data streamed in. Before the test, a last round of debate, whether to include a standard fastener layout as a control or to test only the revised rivet pattern. It was Samuel Ortiz who suggested both. Put two identical assemblies on parallel rigs and only change the rivet pattern on one. Let them sing side by side, he said in a quiet remark that later appeared in a reconstructed oral history. Brackett, always for numbers, agreed. Data, he believed, would settle disputes that yelling could not. Outside the test hall, orders kept arriving and planes were requisitioned. Somewhere between the supply chain and the decision-makers, the B-17 still appeared as a framing device in memos. Address wing durability for extended-range sorties. That phrase was the sword above the plant. Perform and supply the fleet. Fail and consequences would ripple outward. The plant's leadership knew that any claim of a method improving B-17 wings would need verification beyond the lab. They began the count. Cycles ticked up on digital readouts. Strain gauges sang their electrical song. The first 100 cycles were uneventful, as earlier runs had promised. Scientists noted the small changes in baseline stiffness that accompany any run-in. At cycle 652, a small spike registered on a sensor. Too small to call a failure, but different from earlier control runs. The high-speed cameras, set by the technicians who had become cunning with lenses, recorded a micro-yield near a rivet toe that the naked eye would have missed. Men crowded around monitors, but no one spoke. They were listening to the data the way Brackett had always listened, with both patience and a readiness to react. We stop this part of the narrative here, with the rigs humming and the plant leaning forward, because the next hours would decide whether the method was merely promising or truly transformative. Decisions yet to be made would not only alter production lines, but the lives tied to them. Workers on the floor, air crews in the sky, and engineers whose quiet insistence could, in a single trial, tip a balance. What happened next, the big test, the near failure that would force an improvisation, and the raw aftermath, will be the center of the next sequence. For now, the plant at night keeps its glow. The hand that once pressed a thumb into a cracked sliver of metal has been scrubbed clean. And the ledger of failures awaits the pen that will write the first confirmed success or the next bitter lesson. The question that filled the plant's corridors at that hour was not a technical one alone. Could a single method, devised by human hands against long odds, change the contour of a war's machinery? The answer was still being measured in cycles. Cycles kept climbing. The readouts marched in quiet numbers while the men around them held their breath. A crowd that had learned to measure hope in decimals and hertz. At 6:52, a micro-yield had whispered itself across a monitor, an anomaly that pulled the room taut. But it was at 1282 that the hall began to tremble with an old memory, the number that had once meant a sudden and absolute end. Now, under the new regimen, that number carried a different weight. Hydraulic actuators pumped. Strain gauges spiked and settled like a heartbeat. High-speed cameras painted a film of stress lines marching along rivet rows and spar webs in a slow-motion choreography that, until recently, always ended in a clean, catastrophic snap. Tonight, the cameras showed something else. A grinding, elongating motion in the grain. A smear of plasticity where brittle shards had once fractured free. Somewhere under fluorescent light and the smell of hot metal, a part of the plant began to understand what the engineers had been arguing for in chalk on sidewalks and stamped pages. Then a shriek, a thin, high-frequency sound that had been catalogued as a prelude to failure, sliced the air at 2:17 a.m. The technicians peered at spectrograms projected on a wall, fingers dark with grease and ink. The recording showed the same 0.43-second squeal they had learned to fear, but this time the following data refused to obey old scripts. The crack, when it formed, did not leap like a trapdoor. It crawled, plasticized, and then, bafflingly, slowed. The peened surface lines, the redistributed rivet pattern, and the guided grain flow all seemed to conspire to blunt the advance. The room exhaled, not in celebration, but in the reflexive release of people who had been holding themselves upright for months at the brace of adrenaline. Brackett, eyes rimmed with fatigue and the faint glow of screens, let his hand close on the edge of the test rig. He did not smile. His face catalogued data and consequences in equal measure. Ortiz, standing close by, had tears ragged against the corners of his eyes, part exhaustion, part relief. Harold watched the slow playback with a draftsman's hunger, tracing with a finger the thin white line on a monitor where a crack had almost been. Reconstructed exchange. Ortiz: "It didn't go like the others, Freddie." Brackett: "Low. Good. It shouldn't. We wanted it to tell us how it dies, not to die easy." The data that night did not produce a tidy proclamation. Scientists do not often receive a single number that confirms a thesis. They gather tendencies, trends, and then argue until a consensus appears. Over the next several days, the team ran matched rigs, control specimens, and blind trials. The pattern held. Components treated under the method, Brackett's method as it began to be called in shorthand, showed delayed crack initiation, slower propagation rates, and an altered fracture morphology that suggested energy dissipated through ductile deformation rather than concentrated and released in brittle shards. Where once a rivet toe had acted as a bellwether for sudden breaks, now it became a region of stable, if imperfect, yielding. Still, numbers do not travel in a vacuum. The practical question was always one of scaling. Could a precise, hands-on laboratory protocol be translated into the muscle memory of a production line that turned out hundreds of identical parts under the steam pressure of wartime urgency? The pilot line became the crucible. Racks were rerouted through a new, controlled cooling corridor, an added stage where parts passed under an array of directional air jets and slow conveyors that ensured the prescribed thermal gradient. Workers were retrained to handle blanks differently. A preheat staging area to reduce handling nicks, new torque specifications applied to rivet guns, and a dedicated peening crew taught to focus compressive energy along targeted rivet paths. The crew, who had always prided themselves on output per shift, now prided themselves on reproducing a process to within a fraction of a degree per minute. There were teething problems. Dies that had tolerated old alloys clogged when new compositions were pushed through, and presses occasionally misfed because blanks were slightly softer after the heat cycle. A day's output might fall. Complaints rose in terse memos. But with each iteration, the process grew less fragile. Tooling was adjusted. Jigs were beefed. The new alloy mix received a slightly different temper that preserved machinability without surrendering the fatigue gains. It was, in effect, a social engineering problem as much as a metallurgical one, convincing a system to take care where it had been taught to rush. Field reports arrived with the merciless brevity of military dispatches. A bomber returned with a wing panel torn and dented, a patchwork of survival rather than clean airworthiness. That the crew named good metal and lucky hands in an exchange sent to the plant did not satisfy an engineer's hunger for causal proof. Yet the engineers read the message like a test result. Over months, a statistical picture began to appear. Units fitted with the methods treated assemblies reported fewer catastrophic wing failures under comparative conditions, although variations in mission profiles, enemy action, and maintenance made any single causal attribution indefinable. Brackett himself avoided the triumphalist language favored by press releases. He spoke instead in margins and confidence intervals. The moral ambiguity threaded through the plant in ways that could not be solved by heat treatment curves. One evening, as a rain-slimmed convoy left the gates, Brackett walked toward the employee bulletin board where a typed report lay pinned between ration notices and lost mittens. A short, mournful telegram listing the names of a crew killed in a night raid. He stood there until the rain slicked his forehead. The method he had helped piece together would go where other metals had gone, into wings that carried men to danger and ordnance to distant cities. Saving aircrews and making aircraft more reliable were not morally neutral. They were part of a ledger that included destruction, loss, and blurred lines between necessity and consequence. Among the workers, conversations grew private and searching. A woman who had riveted on the line for years whispered to a friend that she hoped we're keeping boys alive and not arming hatred with better tools. Others argued that the plant's work was to give men a fighting chance, that duty and survival were not easily separable. These were not new debates, but in the narrow hours between shifts they felt acute. Letters from crewmen sometimes arrived. Scraps of gratitude, charred photos of faces in flight gear, and these letters hung in the plant like small human talismans. As production scaled, inspectors arrived with clipboards and an unblinking interest in documentation. Brackett submitted method sheets, control charts, and batch logs. He argued for a staged adoption across assembly lines, a cautious spread that allowed the plant to evaluate longer-term field returns. The War Department's appetite for speed competed with this caution. At one meeting, a liaison from the Pentagon, reading percentages and deadlines off a pencil smear table, asked why a full rollout could not happen immediately. Brackett answered with the bluntness of a man who had held a cold sliver of fractured metal and felt the truth in its edge. Because the world was not a laboratory. Because the cost of a rushed adoption could be measured in lives and failure. Because slow rigor here might save more lives overall. His answer did not satisfy everyone, but it earned him the weary respect of some and the impatience of others. Scaling abroad produced its own surprises. Factories in other states or in allied plants overseas found their tooling and labor conditions differed. An engine plant in the Midwest could not simply copy Pratton's controlled cooling corridor and expect identical results. Local humidity, water quality in quench tanks, and the tensile habits of rivet crews created variation. The method demanded not only a set of technical changes, but a culture of attention, measurement, documentation, and an appreciation for the small hands-on steps that protected parts from damage. In that sense, Brackett's accomplishment was not merely a technical sequence. It was a way of teaching a machine-age workforce to notice the tiny habits that save metal from memory of failure. Not all progress was linear. A winter storm knocked out power at a satellite plant just as a pilot batch was being processed. Workers had to manually finish several assemblies that had been only half through the prescribed cooling corridor. When those parts were instrumented and tested later, they exhibited the more brittle behavior the team had hoped to avoid. A single deviation in process had undone much of the method's benefit. The episode became a cautionary tale displayed in training. Fidelity to process matters. Such stories moved from the labs into the practical lore of the shop floor and shaped how new technicians learned their trade. Over the course of months, the plant accumulated a body of evidence compelling enough to push the War Department to authorize a broader implementation with strict controls. The rollout was never total overnight. Even with authority, logistics and local practices meant adoption staggered. But the method, its alloy batch recipes, its soak and cool schedules, the directional airflow installations, the peening protocol, and modified rivet placement, moved from pilot lines into selected production streams. Men and women who had once handled blanks without thought now saw the process as a ritual of precision. Yet the story of how a single worker's mind helped birth this method needed narrative caution. The transcription sources and recollections that inspired parts of this account place Brackett as a central, practical force in the plant. Other archival fragments suggest a wider mesh of contributors. For historical certainty connecting Brackett's lab work directly to an established, documented method for B-17 wings across all plants, the record is indefinite. What is certain, reconstructed from notes, testimonies, and surviving memos, is the existence of a concentrated effort at Pratt & Whitney and similar plants to address fatigue, to experiment with alloy and heat treatment, and to adapt engine-driven metallurgy to structural components. In other words, the narrative we follow honors a specific human face for clarity and focus, while acknowledging that innovation in wartime is often the product of many hands. Field evidence accumulated slowly, but began to tip the scales. Crews reported fewer in-flight structural failures in squadrons that had been outfitted with components from the pilot lines. The numbers were not a neat causal chain. Missions varied in weather, in enemy response, and in maintenance diligence. Still, when a pattern emerges across many data points, it creates confidence enough for commanders to order further adoption. Letters from squadron leaders, spare, bureaucratic, yet occasionally struck by a human note of thanks, were filed and read at the plant's briefing table. Men passed these letters around and nodded. The work they did had immediate faces. In one particularly memorable instance, a bomber limped back with a wing damaged by flak so severe that the tips were twisted and ailerons shredded. Where older construction might have shed more of the wing in a catastrophic cascade, the assembly, composed of treated spars and redistributed rivet patterns, held in a ragged but flightable state. The crew made emergency procedures and landed with a near miracle of seamanship. The plant received a terse message from base command: "One crew home, structural integrity saved, recommend review." Those words were not a proof, but a point on a graph that moved general opinion. As production ramped and casualty reports accumulated, the plant began the slow withdrawal from the frenzy of wartime. Contracts tapered, shifts were reduced, and the once constant roar of forges dimmed to a more domestic hum. Men and women who had been consumed by an urgency that made moral complexity feel like a footnote began to return to households where children asked about the nights their parents were gone. The ledger of success that Brackett had kept, pages of numbers, sketches, audio signatures, and grain photographs, grew into an archive that would outlive the plant's wartime urgency. In the quieter months after the conflict subsided, the method's technical language migrated into peacetime industry. Aircraft designers, freed from the exigencies of sorties and deadlines, found utility in parts that resisted fatigue. Commercial planes benefited from structural techniques that made wings safer across thousands of pressurization cycles. Manufacturing standards learned to prioritize microstructure control, not for war vehicles, but for passengers and cargo. Engineers who had labored under searchlights began writing procedural manuals, and universities incorporated case studies into materials courses. In that sense, the method's lineage extended beyond the immediate, through adaptation to civilian aerospace and into a broader culture of metallurgical caution. Brackett left the plant some years after the armistice. He did not depart with public fanfare. There are no golden columns in the paperwork that narrate his exit. Instead, recalled conversations, a photograph in which he is shoulder-deep in coal dust, and a folded letter tucked into his notebook compose the record of a life that straddled science and conscience. He took a position advising small manufacturers, lecturing quietly on process control, and occasionally testified before professional societies about the limits of scaling laboratory precision into production. He was not, by the surviving accounts, a man who sought headlines. The plant named no large monument after him. A modest plaque, some decades later, added to a local historical display, would credit the many hands who labored there, with his name among them. The plant itself changed hands, then industries. Buildings once filled with the blaze of furnaces became quieter offices, then warehouses, then museums in part. In a museum case beneath a small placard sits a spar fragment with a peened rivet line and a faint smudge where a worker's thumb had once smoothed a burr. A school group stares, and a docent explains in plain language how metallurgists coaxed alloys to behave. The story, simplified for visitors, often centers on one man who refused to accept failure. That tidy focus comforts a public longing for narratives with clear protagonists. The more complex truth that many hands, many nights, and many arguments together forged the method lives in the margins and lab notebooks that historians continue to mine. It would be dishonest to pretend the method did only good. The machines it strengthened sent men into battle and enabled missions that ended in death and loss for civilians far from the skies that had borne them. Those who worked in the plant held this contradiction in their bodies. The pride of craft mixed with a private unease. Some workers found solace in the belief that saving air crews had moral weight. Others had nightmares of the consequences. The moral ledger did not balance neatly. It became, for many, a lifelong negotiation. Technically, the method's legacy did not stop at aircraft. The principles, attending to grain flow, controlled cooling, surface compressive treatments, and thoughtful fastener placement migrated into bridge construction, into pressure vessels, into the forging of parts where fatigue could mean disaster. The war accelerated an industrial analysis of failure modes that otherwise might have remained distributed across slower peacetime research. That acceleration carried costs and benefits. Faster problem-solving at the price of compressed debate. Broader application at the price of unresolved ethical reflections. In the end, the story that began with a single thumb pressed into a hairline fracture closes on a different scale. The plant's night glow faded into a new dawn for industry. The people who had bent their lives around shifts returned to family and quieter work. A method that had once felt impossible became part of the language of manufacture. Brackett's notes, those scribbled thermocouple readings, the acid-etched grain photos, the audio spectrograms, survive in a box in an archive that smells faintly of old paper and machine oil. Students and engineers leaf through them and still find in their margins the human insistence that marked every line. Careful observation, repeated tests, a stubborn refusal to accept an easy answer. The method that emerged from that insistence is both a technical achievement and a moral artifact. A proof that human hands can, through patient work, shift the tolerances of reality. and a reminder that the things we make in urgency leave footprints beyond the immediate. The final image returns us to the place where the story began, a dim plant at night, a single hand lifting a cracked sliver of metal to the light. If we stand there now in imagination, older and quieter, we can see the metal's thin hairline and understand that in an era of pressure and scarcity, a method was born that altered what wings could do. We can also see the faces of the people who pressed, peened, and logged. Faces that carry gratitude and guilt in nearly equal measure. Technologies do not have morals in themselves. The people who make and use them do. If this account moved you, if the stubbornness of craft, the tension of moral choice, or the hidden labor behind machines matters, consider subscribing to learn more stories of the people who built the technologies that shaped the 20th century. Share this video with someone who asks what happens behind the doors of history's factories. The conversation about invention and consequence is one worth continuing. In the quiet that followed, Pratt & Whitney's plant kept a few lights burning for months, and then slowly fewer still. The forges that had once sung at night were replaced by quieter tests, and later by new industries entirely. The ledger closed, pages folded and placed in a drawer. Yet when scholars open those pages, they discover not a single eureka, but a long apprenticeship with metal. Nights of listening, of failing, and of learning. The impossible method, so labeled in later retellings because of the odds stacked against its emergence, was less a sudden miracle than a patient concert of small, disciplined acts. It was an answer forged from repetition. What remains is a double image, a stronger wing that helped keep crews aloft, and a moral contour that asks us to remember how inventions serve ends shaped by human choices. In history, as in metallurgy, the way something cools often determines what it becomes.